recording. Oops, I hit the wrong one. Now I have to back up again. Sorry about this. We'll get there. I had the right slide and everything. Now I have to wait for this again. Let me turn over the projector. Got one more announcement. I was going to put it on Screencast-O-Matic once we were recording, and we are now recording, so let me put it out there for you. Okay. There was a button. Yeah, I hit the wrong one. Okay, and start the slideshow from current slide. Okay, now finally we're going. Here's the last announcement. Sorry about this one. Sort of a good news, bad news situation. The bad news is I will be out most of Thursday and all of Friday. So I have office hours on Thursday from 12:15 to 4:45. I won't be here. And Friday, 7:45 to 11:45, I won't be here. We've got a wedding in Dallas, Texas, and our flight's out Thursday afternoon. So the good news, though, is it won't affect this class any. We meet Monday, Wednesday. All right, so we won't lose any class time. I knew that would please you, right? All right, so, but if you're looking for me Thursday or Friday, I won't be. I'm planning to come in Thursday morning and teach my 8 o'clock class, but then I've got to leave right after that because you have to be at the airport so early, before the flight for security and all that. So anyway, just wanted to let you know that. Next, your questions. Do I need to get the test in front of me? Tell 2. Second, here's first test. Okay. All right, what were the questions? I'll probably write on this slide just because it's more difficult getting anything else to come up. So if you get the questions, I'll try to answer them. What's that now?
The first one?
First one.
Yeah.
L'Hopital's rule?
Yeah, L'Hopital's rule. When we find the L'Hopital's rule, just like, we find an antiderivative and then plot the value of x, right?
Okay. Let me go on and write this down. It says, evaluate the following limits using L'Hopital's rule and the fundamental theorem of calculus, part 2. And here's the first one, the limit as x approaches 0 from the positive side, from the right-hand side, of, and here is your limit, the argument for the limit, 0 to sine x of the square root of 1 minus t squared dt over x. Okay, yeah. Hold on just a minute. Now, L'Hopital's rule works when you have in what they call an indeterminate form. And when it's a ratio like this, it needs to be 0 over 0, or in some circumstances, infinity over infinity. Those are a little stranger, but this one, obviously your denominator as x approaches 0 from the right, that's going to be approaching 0. Well, what happens to the numerator when x approaches 0 from the right? Okay, sine of x is, sine of 0 is, when x is approaching 0 from the right, what is sine of 0? 0. So you've got an interval that's going from 0 to 0. It doesn't matter what that is. That's approaching 0. Okay, right? You agree? So this is the form that we can use L'Hopital's rule, and it says use it, okay? Well, we just verified it, we can use it. So what we're going to do, what does L'Hopital's rule tell you to do? If you have an indeterminate form, specifically 0 over 0, indeterminate form, not anti, you take the derivative of the numerator and the denominator, and then take the limit again. Will that do it for you? Right.
What about the limits that the zero to sine x is confusing me. Like when we do the L'Hopital rule, we didn't have something like.
Okay.
We just like find the derivative and then plug the value of the x.
Okay. Okay. When you take the derivative of this with respect to x and the derivative of that with respect to x, okay, that denominator is easy, right?
Yeah.
Yeah. Okay. So what you're doing here, and I should write it out, but I'm not. So you're taking d by dx of the numerator and d by dx of the denominator. Okay? Now, that's L'Hopital's rule that tells you to do that, because it's in determinate form. Now, the fundamental theorem of calculus part 2 tells you how you can do this evaluation, right?
Yeah.
Okay, so you know what to do with that then. Okay?
Which take the antiderivative?
You know, you're taking the derivative of this thing. Okay? Now, find the fundamental theorem of calculus part 2. That was in chapter 5. 5.5, I believe it was. Okay. Now, Theorem 1 on page 295 gets you started, but it's not quite what we're doing here. What you need to do it's the fundamental theorem of calculus and the chain rule, which is like example 4 on page 297. Now, your book probably has different page numbers, but do you see example 4 on section 5.5 somewhere around page 297? It may not be that page number.
Okay. Example 4.
Yeah, in 5.5.
What is that?
Does it say the FTC and the chain rule? What is the title of your section 5.5? What's the title of it? Top of the page.
Net change as the integral.
Okay, right. Okay, you need to go back to 5.4 or up to 5.6.
Fundamental. Do I need to go to fundamental
Okay.
theorem
Part
part 2?
2, that's it. What's your example 4 there? Do you have an example 4?
Yeah, the chain rule.
Yes, that's it. Okay? Now you see what we have here is a function not with x squared up there, but with sine x up there. Okay? And what you need to do is treat it like example 4 there. I don't want to do too much to give it away here. But if you follow that logic, that's what you're doing there. Okay?
So we have to use the chain rule. We have to use the chain rule for the.
Yes. Yeah, exactly.
And then
Yeah.
from the value of 0 and sine x.
What's that now? Okay. Here's, I'll kind of follow the way they're doing this. They say that g of x is a composite function, like our original thing here was a composite function of a of x squared and x squared. And without going into too much there, you see that g prime of x, which is what we're doing here, g being the integral, the g prime of x is equal to and that's what we've got here. Here is where you use kind of, your first question was, it's kind of like, they are using a substitution here, okay? And here's what the substitution here is. Most people like to use u equals sine x, okay? All right, and then you'll need to know du is equal to what? Not minus, it's cosine x dx, okay? Now, okay, right. We're not messing with the interior part of it. We're just messing with here. You see, fundamental theorem of calculus, if you turn back to one page there, in fact, that is actually at the top of the page there. But if you turn back one page for theorem 1, a of x is equal to the integral from a to x of f of t dt. Okay? When you take the derivative of that, you get just f of x. Whatever your f is, right? You don't have to do anything to change the f. You just plug in the x for the t. Notice that's what it's doing. The derivative, let me write this down. The d, this is fundamental theorem of calculus part B, is, they put an a here, so I'll put an a to x of f of t dt. Okay? Fundamental theorem of calculus basically is saying if you take the derivative of an integral, one undoes the other one, and you're left simply with f of x. Okay? Now, the problem with this one is that integral hasn't got an x there. It's got a sine x there. Okay? That's somewhat of a problem. Okay? So, and I don't think I actually needed this du here, did I? I wrote it down, but I don't. Well, yeah, we ultimately will. But we'll get there in a second. So what we're changing this to, and I'm not going to write the limit part, but we're changing this to d by du of the integral of from 0 to u, because u was sine x, and this will still be the square root of 1 minus t squared dt. Okay? Say again? I can't hear you. And what I still do? Oh, over x. Yeah, over. Yeah, we're not going to worry with that. That's still going to say dx over dx of x. Yeah. Okay, we'll come to that. But I'm just worrying about the numerator here. Okay. Now, where do we go from there? What this shows us here on page 2. Well, in example 4 of the fundamental theorem of calculus part 2 part. I think it's your 5.4, your 5.5. Okay. What it shows you here is then that numerator is this. Okay. Now that's not the same as that numerator. You have one big difference here. You got a du dx. Okay? So basically, what we do here, now the trouble is they got signs in different places here, but the f of t here is the same as that f of t there. Well, what does this tell you this is? Shock. Okay. This tells us This thing right here says all you do is plug the u in for t. That's what you did with the fundamental theorem of calculus part 2. If you're taking the derivative with respect to x of something with x up here, t's here, you just, the derivative of an integral sort of cancel each other out, and you're left with f of x. Well, now we've got derivative with respect to u of this. Now, that's not what we had up here, but what we had up here is d by dx. Well, d by dx is d of this by du times du dx. That's the chain rule part, okay? So, this thing looks just like this, where your f of t is the square root of 1 minus t squared. Okay? So basically what you do is plug the u in for t, just like you plug the x in for t there. Okay? Okay, no. In the book that was sine x, here it's the square root of 1. So this gives you the, I think I know what you're asking now. This gives you f of u, that f of u. So it's the square root of 1 minus u squared. Right? Okay. Times du dx. Well, du dx is cosine x dx. But if this is what you're asking, it's exactly right. Sorry. Okay? Plug in what u is. U is sine x. So this is the square root of 1 minus sine squared x, right? And that is, what's 1 minus sine squared x? Cosine squared x. Square root of that is cosine x. So this gives you cosine squared x. Oh, we don't need a dx out here. I'm sorry. Du dx, you write it this way. Du dx is equal to cosine x. So you don't need this du dx out there. So you just get cosine squared x. Okay? So what do we have? We now have the limit of cosine squared x over, and what's the derivative with respect to x of x? 1. Okay, now you take the limit of that as x approaches 0 from the positive side. You've got your answer.
Then we take the limit of that.
Yes.
What happened to the cosine over there?
Okay. Right here. This one, du dx is cosine x. So this du dx is your cosine x.
Yes.
This part here is f of u, which is the square root of 1 minus u squared. But u is sine x, so u squared is sine squared x. 1 minus sine squared x is cosine squared x. Square root of that is cosine, so this gives you a cosine, that gives you a cosine, that's what gives you a cosine squared. Right? Okay? Does that make sense? Okay, does that answer your question? I'm sorry, I carried it way too far probably, but do you see how to do this?
Yeah.
Okay. And by the way, one of the questions on the practice thing that we were doing in the math team was not the same problem, but one similar to it. One similar to the one that was in the book of fundamental theorem of calculus, but with a function up there rather than an x up there. So if you had been there for that, this would have made a lot more sense. Okay. Any others? Yeah. That's right.
I really don't understand chapter 5 that good.
Okay.
Yeah.
That's that.
I said I don't really understand chapter 5 that good, so the text is
Okay. All righty. I think just about every class I say, now, are there any questions? And it seems like in chapter 5 that would have been a good time to say, I don't understand this at that time, but if there's anything specific, I'll try to, like I just did this one, I'll try to help you with it, but I don't know what else to do.
Until you're doing this, I didn't know we can take you as, we can equal you to the sign X, you know what I mean? I
Yeah.
always think we can equal you to the whatever is inside.
Right, but you see, if you look at that example 4 in that section on fundamental theorem of calculus part 2, they did that very thing. They said, set u equals what the upper limit is. And the upper limit here was sine x. The one in the book was x squared. And it's the same thing from there. It's not quite the same as the substitution on the other. You should do it a little differently, but yeah.
The second one.
Okay. Is this question 2 or the second part of question 1? The B part of question 1.
We can do the same thing like B part. I can at least try.
Okay, the B part is very much like the A part, except now your U is tangent x, right?
Yeah.
And you go through the same deal there. Now, you've got to first make sure that it's 0 over 0. Well, let's see if it is. When x approaching 0, tangent of 0 is?
Tangent 0.
Yeah. Tangent of 0 is 0. It does like this, okay? Because it's sine over cosine, and sine is 0 and cosine is 1 is 0. So it's 0 over 1 is 0. So the numerator is approaching 0, and the denominator, as x approaches 0, sine x is approaching 0. So you got a 0 over 0. L'Hopital's rule works. So you do derivative of numerator and denominator just like we did here. But now, rather than sine x up there, you have a tangent x. So you do let u equal tangent x, then du dx. Don't do the dx over there. Du dx is equal to whatever that is. You have to do that. And then proceed with this. Then, once you get it into that form, du dx of integral from 0 to u, then that happens to be a 1 over 1 plus tangent squared. T squared. It just becomes 1 plus u squared. Right? 1 over 1 plus u squared. But then your du dx is whatever your du dx here. When x is tangent x, you have to figure out what du is. Du dx. And then you plug them back in just like we had before. And take the derivative of the denominator too as x approaches 0. So very much the same type of problem, just different functions in there. But do it. Are you confident enough to do that, or do you need to do this too? What's that? Oh, you want to do that one too? Okay. Now I'm going to be real lazy about this. Okay. And basically, the only thing that's changing here is it's not 0 from the plus side, and this is a tangent, and this is a goodness, this is slow. Okay. Goodness, it's really slow. Okay. I don't know what that is, but I'll get rid of it. This changes. That changes. All right, I think we're ready. Let's see if I can write it now. The question is, limit as x approaches 0 of, forget about the d by dx, just pretend it's not there yet, the integral from of 0 to tangent x of, I'm just writing this a little bit differently, 1 over 1 plus t squared, okay, and the denominator is 2 sine x. Okay, I think that's the same, it's just they wrote it dt over that, I just wrote it 1 over that dt. You buy that? Yeah. Okay, now you tell me. Okay, and we've already done the first part again, forget about this. You evaluate this as x approaches 0, that would be a 0 here, and that's a 0 there. So yeah, it fits the indeterminate form, so you can do L'Hopital's rule, which says take d by dx and numerator and denominator. So what is d by dx of the numerator then? You can't do it, not by fundamental theorem of calculus part 2, because that's not an x, it's a tangent x. So what you do is do a substitution and let u equal what? Tangent x. Very good. Okay? Okay? Now, what's du dx? Okay, what's derivative of tangent, not of sine? No, derivative of sine is cosine. Derivative of no, it's not cotangent. Okay? Let me see if I can find it quickly. I don't think it's in the front. Or is it? No, those are just your formulas. I think it's in the back, but let me see. In the very back of your book, you have some stiff cardstock pages. The last several of those are your integrals. The one right before the integral page is a differentiation page, and it says trigonometric functions. You see it? Number 15 says d by dx of tangent x is secant squared x. Okay? So du dx is secant squared x. Okay, secant squared x. All right. Now, what we were wanting was derivative of that, but we've changed that to this. So you have d by du, and now we've got the u up there, the 0 here. That part stays the same. 1 over 1 plus t squared. This is nuts. This thing is so nuts. Okay. All right. Then this thing, d by du of this times du dx, that gives you d by d that. Yeah, that's the same expression as that, with the trig substitution in it. I mean, the u substitution in that. Now, we got to do that. The denominator. What is the derivative of d by dx of 2 sine x? I think I'll go on and take this out because I don't think you need it anymore. What is d by dx of 2 sine x? Okay, it's 2 cosine x, right? Derivative, okay, you can pull the 2 outside, because that's just a constant, and derivative of sine to cosine, right? All right, we just got to figure out what that numerator is. Fundamental theorem of calculus part 2, the reason we did this, that makes that a piece of cake. What is it? You're taking the derivative of an integral with the same argument here. That just makes saying this is, see, this is integrating this, then this is taking the derivative of that integral. So the derivative undoes the integral, just leaving you this thing, but with u substituted in, right? So that gives you, this is fundamental theorem of calculus, part 2. It gives you 1 over, you tell me, 1 plus, no, u, yeah, okay. It's 1 plus u squared, because that's what you plug in, but u is tangent, so it's 1 plus tangent squared theta. X, I'm sorry, x. I'm so used to using. Yuck! This thing is such a pain in the neck. There we go. I hit the wrong thing. All right. Tangent x. Okay. Yeah, tangent squared x. I had it down there and I erased it by mistake. Tangent squared x. Okay. Now, times du dx. Du dx is secant squared x. Right. Right. Okay, we just determined that. But what is 1 plus tangent squared x? It's what? 1 plus tangent squared x. I think that may be on the front inside cover of your book. The first page is algebra and geometry. The back side of that is trigonometry. And where are your fundamental identities? There we go. You see on the right-hand top column, 1 plus tangent squared theta is secant squared theta, absolutely. So you have this in the denominator is a secant squared theta, or secant squared x. And that's a secant squared x, so what does your numerator become? 1 over 2 cosine x. Well, what is cosine x is approaching 0, because that's the limit you're taking. Yeah, cosine is 1, so that would be 1 times 2 is 2, so you have a 1 over 2. Yeah, I took it too far. Do you see that? You got it? Yeah. Sorry, I took that way too far. Do you see what happened there? Okay. Now that next one almost looks like it's wrong. This is number, what, 2? Yes, that's a d by dx, not d by dt. Sorry about that, folks. I don't think that was doable with a d by dt. I should have caught that earlier. So let me put this on the board for whoever may be listening to this. Okay? My pen's not working. Okay, now it's working, I hope. Number 2, this is Cal 2 Test 1. Number 2 is calculate d by dx of the integral. Goodness gracious, this pen is so slow. Log x squared. That's from pi to that. It's really ugly. Sine cubed t dt. Huh. Okay. Sorry, I mistyped that. It can't be a t down there. It has to be an x. It's still looking bad. So let me change. Ha! This thing is so aggravating. Okay. Okay. Trying to. Okay. dx. That's a dx, and this is a pi. Okay. Hopefully that's more real. Now, this isn't L'Hopital's rule, but it's the other part. It's just fundamental theorem of calculus part 2. And don't you see that's basically, except for the L'Hopital's rule, it's the same thing as we were doing before.
So we have to use the method u equal to
And what will u equal?
ln x squared.
Yes, exactly. Okay? So let u equal log of x squared. Now this is a double chain rule, right? Then, now remember here, you don't do du, you do du dx. Okay? And what's du dx? Okay? Got the 2.
And we write the ln x.
Okay, now, okay, it's not the log of x squared. Log of x squared is log of x squared. So
The log of x is 1 over.
the derivative of log is 1 over the argument. So that would be a 1 over, I'm going to leave the 2 there because I'm going to want it later, 1 over x squared. But then you got the chain rule for x squared. That would give you, derivative of x squared is 2x, right? So this gives you 2 over x. You see it? That's du dx. All right. Now, if I were going the other way with that, and you started out with du dx being 2 over x, then that would be du is equal to 2 over x dx. That would be log of 2 times the log of x, but 2 times the log of x is the same as log of x squared. So yeah, that is exactly right. Okay? Now, once you have that in there, you have then d by du of the integral of pi, and it doesn't matter what that lower integral is, that of sine cubed t dt. That's with u put in there, but you still need to have a du dx, so you can have d by dx of this. Because you can think of that as the u's canceling out. This is what really the u's canceling out. This is d by dx. This is the x. Right? And what would this thing right here be then? Fundamental theorem of calculus part 2 tells you this is what? fundamental theorem of calculus tell you. You take the derivative of an integral, they undo each other. As long as this and that are the same, they are. And what does that give you? What did it give you on the last few problems? Well, go back to that page, the theorem, what was it, theorem 3? Yeah. In the section Fundamental Theorem of Calculus, Part 2, Theorem 1. Where you have d by d something of the integral of something to a number to the something you have there. Oh. Yes, that'll be sine cube u. Exactly. So that, ooh, I got the wrong pen. This thing right here is simply sine cubed of u. Exactly. But of course, what is u? Of x squared. Okay? And your du dx is 2 over x, so I'm going to write that down, 2 over x. And this just becomes sine, well, I'll let you finish the problem. I'm doing too much of it. But you said it right. And then your du dx is 4.
And we can use the chain rule for that?
No, you've already used it. You used it when you did this. In fact, you used it twice when you did this. Okay? Now you're just plugging back in what u is. There's your u. You put this instead of that, and then you've got that, and basically you're done with the problem. You have a little bit of cleaning up to do, but that's it. All right? Do you see why this is true? That fundamental theorem of calculus part 2. They're loving it here, okay? They're using it over and over and over again. Okay? Any others?
I did the 3, I'm not sure I did right. But what I did is I got the rate of like 1 flows into a, the first, I got the antiderivative of the first one.
Okay.
And I got that into the, I basically got the value of in between 1 and 5.
Right.
And subtract, get the value. And I do the same thing for the making.
Right.
And then subtract the
Right.
and get, yeah, that's what I did. I think
That sounds reasonable. Okay. You okay with that one too, Marcus? Okay. How about number 4? What's that? Okay. All right. I'm going to refer you to, you got the water leak one, right? Integral of velocity. This is, I hope it's section, probably a different number. Says the net change in the integral is the rate of change. That's 5 in U. Is that right? In your book? Okay. And theorem 2, integral of velocity. Okay. Distance traveled over an interval distance travel over an interval. You got two objects. They're starting from the origin. Same time, t equals 0. They're at the origin. You find how far object 1 moves in that time, how far object 2 moves with that velocity, and make the difference of them at the end. Okay?
So interval between 0 to 15.
Okay? All right. Let me go and erase this. All right. Now, what were you saying?
The object 1, we get interval.
Okay. So let's just call D1 how far the first one moves in those 15 seconds, I guess it is. It doesn't say what the units are. Time t equal 15. D for object 1 would be the integral from, what's your t going from and to? 0 to 15 of 1 over the 4th root. Now, I don't like the form, so I want to change the form, and y'all tell me if I'm okay with this. Okay. Okay. That would be t plus 1 to the what power? Second? I'm not sure how you got that. I'm just doing the first one. Huh? Wouldn't that be it? Wouldn't that be it? I didn't write down the first. I should have, I guess. 1 over the 4th root of t plus 1. That's what we're trying to do, right? And that would be the same as 1 over t plus 1 to the 1/4 power, right? And since it's in the denominator, you can move it to the numerator and make it the minus 1/4 power, right? And don't you think you can go from there?
Yeah.
Right.
And find
The value of the integral there.
and what about
The second one, that would be d2 is equal to, from the formula from before, integral from 0 to 15 of, this one I'd write how? T plus 1 to the 1/2 power. Okay? And that,
subtract?
yeah, once you get the two distances, take the difference between them. And you have how far they are apart. Now you could write that as an integral of a difference. Man, this is easy, I think, to take.
Basically, the same thing. What we did the same thing for number 3 and 4 is the same, right?
Yeah, well, yeah, it's just that you got different functions, yeah. But yeah, if you look at the net change, you would have the net change in S of t, which S of t here is the quantity of water, excuse me, I'm having trouble breathing. The quantity of water, yeah, it's a flow rate times an elapsed time. Quantity of water is a flow rate times elapsed time. Well, your flow rate here is 1,500 plus 7 t squared gallons per hour that's coming in, but then you have a leak that's going out at 4t plus t squared gallons per hour. So yeah, you do and the flow rate is your, that's your flow rate, and then the time elapsed is your dt, and you're integrating that. So yeah, it's very, very similar. It's just, yeah, and you take the difference of the two. You can do them separately or you can do them together. That one may work together a little bit easier than this one did, because when you subtract, you lose one of your t squareds. I mean, that'd be 1,500 minus 4t plus 6t squared. And that may be easier to evaluate than doing them separately. But it's not much difference. They're pretty close to the same. What's that?
I was just asking, we take the
Yeah, right. And you can probably do that almost directly, but even if you can't, you can do a real simple substitution, but it just depends on what you prefer to do. If that was a t squared or something like that, yeah, you'd have to do a substitution. But it's not, it's just a t plus 1. But if you want to do that as a substitution, you can, and then change the limits and stuff. It's pretty easy. Either way, I think. Okay.
What about the
Number 5. Okay, there we're getting into what you reckon. How do you reckon we're going to approach those?
Take the antiderivative.
Okay. But what technique? Substitution. Yeah. Every one of those is a substitution. Okay. You just got to be a little wise or careful about what you're using to substitute. Can you do those okay, or?
Yeah.
Okay. That's number 5, and I think, what's that? Number 6. Number 6 also is a substitution, I'm pretty sure. Yeah. A and B, right.
Okay, I did the 7A, and when I'm doing 7B, I use the substitute.
Okay. I'm sorry, I can't quite understand. You talking about 7 and 8?
Can you do 7B, please?
Oh, 7B. Okay. All right, 7B. All right, for me to erase what's on the slide now? Okay. So this will be 7B. Use a change of variables formula to evaluate the given integral. Okay? And this will be from, pretty sure that's the 0 to 1. Of x cubed times the square root of 1 minus x squared. Sorry, dx. Sorry, my screen is flopping around on me. So we're going to need a change of variables. What you reckon is going to be our change of variable here? And basically, this is a lot like a substitution. It's just a definite integral. What would you do?
I did the same thing, that let u equal to 1 minus x squared.
That's what I would try first. Let u equal 1 minus x squared. Good. Then du equal minus 2x dx. Now you put the dx out to the side there.
Yeah, and then divided by 2 minus.
Right, divide by minus 2. Okay, so these go out. So,
What about, like, we got the x cubed in front?
uh-huh.
We just get the x.
Okay. but you really want just an x. Well, what do we do with the other, that x squared that you have left over there? This accounts for the x dx. You still got x squared that you can't account for, right? But what does this tell you? Say that again.
I think we can get the x value like by doing u equal to 1 minus x squared, and we get the x value from that.
Okay. Solve that for x squared. Other words, add an x squared to both sides.
Yeah, that's what I'm trying to say.
Okay. And that gives you u is equal, or u plus x squared is equal to 1, right? And then subtract the u from both sides, and you get x squared is equal to 1 minus u.
So we get x equal to 1 minus,
X squared is equal to, no,
we just need x squared.
because that's what we want, the x squared. You had an extra x squared here. When you had to take out the x dx, you just have an x squared there.
We have the x cubed over there.
Okay, but one of those x's goes with the x dx, right? And that leaves you an x squared, right? I'll write it this way. The integral from 0 to 1, I'll leave that for now. I'll write this as x squared, the square root of 1 minus x squared, x dx. Isn't that the same thing? That's what you have up there? I took one of those x from x cubed and moved it over here, right? This is just x times x squared, right? X cubed is x times x squared. Okay, I take the x and move it with the dx, okay?
Yeah.
And that leaves you an x squared times this, right?
Why we still keep 1 minus x cubed?
Okay, I was just rewriting the very first thing here as, and maybe I should have done x times x squared times 1 minus x squared dx. Would that have been better? Okay. Okay. All right. Okay. Isn't that the same as that? Right? Right. Now, what I'm going to do is split this into 3 parts. The x squared part, the square root of 1 minus x squared part, and the x dx part, moving this over to that. They're all multiplied together. Okay? So then, so if it's okay to do that, I'll do it here. I'll just take this and move it over here. So it's no longer there. Right? Now I'll do the substitution. I'm not going to change my limits yet. I'll change them in a second. And this will be, what was x squared? 1 minus u. And then your 1 minus x squared, that's u to the 1/2 power, because it's the square root of that thing, right? And then it's your minus 1 over 2. I'm going to take that on the outside, du. Right? You see that? Okay. Now, we need to change our limits. The x is going from 0 to 1. Well, when x is 0, what does that give you here? When x is 0, what does this give you? 1. Okay. And when x is 1, what does that give you? 0. Okay. Now, I usually don't like to have the bigger number on the bottom and the smaller on top, but if I flop those, what does that do to my integral? Change it to a minus. Well, it's already a minus, so that changes it back to a plus. So this is plus 1/2 the integral from 0 to 1 of 1 minus u times u to the 1/2 du.
What happened to the x?
The what?
We took the x out?
What x? The x that was here?
Yeah.
Okay, I moved it over here with the dx.
Yes.
And this x dx is the negative 1/2 du. So for the negative 1/2 here, the du there, the du, it was the x dx. Right? Does that make sense?
I'm sorry.
No, it's fine. Take all the time you need. Now, if I'm skipping too many steps, put in whatever you missed, okay? Is that all right? Now, before I would integrate, I would do one more thing. What would that do? Here we have a monomial times a binomial. Distribute. Multiply both of those terms in the binomial by the one term in the monomial. Then you can integrate. And it's fairly straightforward integration. Right? Feel like I'm doing an awful lot of these problems. Y'all are telling me what to do. We have to argue a little bit, but you know, okay. Is this making sense? Can you take it from there?
Yes.
Any others?
Yes.
Which?
8A is kind of hard. Like
8A? Is that what you said? Okay. Wait just a second. Let me erase all the ink. I'm sorry. I should have asked, was it okay to erase all the ink? But I've already done it now. All right. I've got to read what that is. 8A. This is the integral from 1 to e of log x dx over x times the integral of 1 plus log squared x. I think I wrote it right. Right? How would you approach a problem like that? Most of what we're doing in chapter 5 been doing. We had the fundamental theorem of calculus, we finished with those problems. Just about everything else was substitution. So you just got to figure out what you reckon we need to use as a substitution. That sounds like a good idea to me. It may not work, but let's try it first. Let, you want it to be u? U equal, and what did you say?
1 plus ln square x.
Okay. Then what's your next step? Du, or the differential anyway, is equal to, say again? Not quite yet. Yeah, it will be. Okay, I'll put it that. 1 over x times. Well, what did you do with the squared there? Yeah. Here's how I would have done it. And I thought maybe you were doing the same thing, but here's how I do it, because I do it. I have to make sure I do each step. Okay. Derivative of 1 is 0, so that's gone. Okay. The outermost function here is the squaring function. How do you take that? It's 2 times the log of x, ln x, to the first power, times derivative of 1 over x, because derivative of log x is 1 over x. So this gives me 2 log x over x. dx, I'm sorry. I left that part out. All right. Now, notice what we have here. We have a log x over x. So all we have to do is divide out the 2 here and the 2 there, and you got it now. There is your log x dx over x. Exactly what you got there. Is that enough to go on?
Yeah.
Okay. All right. Any others?
I believe the B part also we use the substitute method.
I would guess so, yeah. I think it's a pretty straightforward substitution.
And the 9A also we use the same method.
Okay. Now, 9A obviously has an inverse cosine in it. You see it right there. And the inverse cosine, it's now remember that inverse cosine does not mean cosine to the negative 1 power. That's inverse cosine. Okay. Now, where I would go to look, yuck, they don't have them here. They have the trig functions, but they don't have the inverse trig functions. Okay? Not in the front. Okay? In the back, I'm pretty sure they do. Okay? Inverse trig function, and you're doing an integral here. So let's see. Oh, here we go. All right. Derivative of the inverse cosine. If you look on the differentiation, the pages in the back, number 20, derivative of inverse cosine. So that would lead me to say, let u equal inverse cosine of 3x. And then do d by dx from that, and I think you'll come something very close to what you got down there. No, maybe not quite, but close enough that you can go from there, I think. Do you agree? Okay, that's the substitution I'd make there. And the next one, obviously, is the inverse tangent. So I think I'd do the same approach and let that be the thing I'm substituting. That one the wrong section. Here we go. Inverse tangent function is number 21 in the back. And you see you wind up with something not the same, but somewhat similar to what you got down there. You might even have to have 2 substitutions there. I think you probably would. Might have to do e to the x first, and then you get an inverse tangent of u and something in the denominator, and then do another one for the inverse tangent. Or at least that's what I would try first. Make sense? Okay?
I think we're using the same method for 10.
Number 10, going to be very similar. Yeah. I think the first substitution probably should be your inverse sine. The trouble is I'm not seeing that quite as easily now. And in this case, that's maybe just a slight bit, I want to say trickier, but that may not be the right, no, I'll take it back. Go back and make a substitution of your inner part, let U equal cosine X, okay, then do your inverse sine of the U. I think that's the way you have to go about it. And then hope things will pan out. Okay. You okay with that then? So no more questions on the test. What's that? Yeah, these are not trivial. They're definitely not trivial. Okay. Now, how are we doing on time? I've got a sneeze, I'm so sorry.
We got 7 more minutes.
Sorry. What'd you say?
7 more minutes.
We got 7 minutes? Okay. We don't have much further to go. Well, I lost my place. Right? Did I? Yes, I did. We're in chapter 6, 6.5, work and energy. I did lose my place. Here we are. I had it right here. Let's see if we can get any of this done. All right. Okay. One typical calculation involves finding the work required to stretch a spring. Now, again, what we were talking about before, we were talking about work in general, and the general thing, work is force times displacement. Okay? And if the force is a constant force, then you got constant force times displacement, which may be your variable dx, but it's a pretty easy thing to do. But if you have a variable force, F is a function of x times dx, then you have to do an integration. And that was the last slide we had before this one. That's the definition of work. So one typical calculation that has work as a variable of the displacement is the work against, an elastic medium. And this is what Hooke's law is talking about. I'm sorry, my throat is going. Okay, if this is your equilibrium position, we'll call that x equals 0 down here, and you stretch the spring, what's the spring going to be doing to you? Pulling back that way, right? That's called the restoring force, the restorative force. So the restoring force is minus kx. Now k is your spring constant. That's your, they usually have to give you one sample of that, and then with that as a sample, you calculate k, and then you do your problem from there on. So that's your restorative force. Now, if you pushed against the spring, then what's the spring doing? Pushing back that way. So you've made your x negative, but now the force is minus that. It's pushing in the positive direction. This when you pull a positive x, it's pulling you backward in a negative direction. So that's why it's always a negative kx. That's Hooke's law, and that is, by the way, a variable force. Because if you pull it x, that's pulling back minus kx. You pull a little more, it's pulling back harder. Okay? So that's why it's a variable force, because it varies. You pull just a little bit, and it just pulls back a little bit. So that's a variable force. Okay? According to the amount that it's displaced. K is the spring constant. And if we want to stretch the spring further, let's apply a force F equal kx to counteract the force exerted by the spring. So here's example 1, Hooke's law. Assuming a spring constant of, and as soon as I go to write, of course it's going to, there we go. Okay. Assuming a spring constant of K is equal to 400 newtons per meter. Is that what yours is? Okay. There's the K of 400 newtons per meter. Find the work required to A, stretch the spring 10 centimeters beyond equilibrium. Okay? So we want to stretch spring 10 centimeters beyond equilibrium. Okay, so we'll imagine that X there down there is equal, it's going up to 10. Okay, 10 centimeters. Now, do you notice a little something wrong, bothersome about this problem? Second? Okay, yeah, your units don't match. This is in newtons per meter and this is in centimeters. So you either have to get this to newtons per centimeter or get that to meters. Which way you want to go? Yeah, this is easy to get to meters. How many meters is 10 centimeters? It's what? 0.1, yes. Okay, so this is 0.1. If you want to put the extra zero, you could. I don't think it's necessarily meters. This is a math book. They're not caring about digits, So that's the same as a tenth of a meter. Okay, so now I think we can go with that. Okay, assuming spring constant, so we're assuming Hooke's law applies here. So what does the work equation or formula or definition tell you? From 0 to 0.1. Okay, your 400 is your K, so I'm going to pull that on the outside. That's newtons per meter. Okay. It might be helpful to write down what the force is. The force is, now, they can be just a little sloppy with the signs here. They'd say F equal Kx, which is fine. What they're saying here, find the work required to, if you're stretching the spring, you're doing work against the spring, so it is a positive force, okay? And the K is that, so you have an X dx, right? Because the force is Kx, so you plug that in, Kx dx, put the K on the outside. Okay, so what is this? 400 times antiderivative of x dx. X squared over 2 evaluated from 0 to 0.1. Pretty small range there. First thing I'm going to do is get rid of the 2 here and make this 200, because that's going to be multiplied by everything. So get that out of the way. So this will be 200 newtons per meter times, and you plug in the 0.1, that would be 0.1, exactly. 0.1 times 0.1 is 0.01, and I can do the 0, and that's nothing, okay? So here's what we got, and this would be what? 2 Newton meters, which would be 2 joules. Now, I sort of glossed over the units there. This, remember, was newtons per meter, but you're multiplying by meter squared, so that's why you had a 2 Newton meters left, which is 2 joules. Okay? Is that all the time we have? All right. We didn't get far today. I think we got a lot done. And y'all are okay with what we did? Okay. Now, I was prepared to give you your test for Chapter 6, but since we didn't quite finish it, we'll hold off of that, and we'll start with B next time. We moved on the baby steps today. Okay. So, let's see. I think I can also give you maybe a homework problem or two. And please, hey, work these homework problems. If you're having problem understanding, then ask me then rather than having to catch up at the test. Okay. So homework exercises here, I think we already did 1. And now I think you can do 3 or 5. You might be able to do 7 now too. Might be able to do 9. I think we'll stop there and pick up the rest of those later. All right, good deal. So we'll see you Wednesday. Remember, I will not be here Thursday after 9:30, maybe even after 9:15, and all day Friday. So, all right, let me turn off screencast